Okay, the equations we need for this worksheet include intensity is power over 4 pi r squared. That's the equation we use for waves that spread out spherically, because when we do power divided by area, the area of a sphere is 4 pi r squared. Another important equation, power is the energy divided by the time interval. We'll also need speed of light, or any wave speed, is frequency times lambda, wavelength. And lastly, we'll need intensity is equal to the incident and transmitted intensity equals incident intensity times cosine squared of the angle between the polarization plane and the filter's axis. So that's Malice's law. Number 1. At a distance of 5 meters, a wave possesses an intensity of 30 watts per meter squared. Calculate the intensity of the wave at a distance of 10 meters. You might think to use this equation, but there is no filter, so instead we're going to use this one. Now we have to assume that power is constant. And that's true as long as there's no damping or objects standing in the way that absorb some of the power. Okay, if power is constant, there's two ways to approach it. You could say the first intensity times 4 pi times the first r squared equals the same power that you'd get when using the second values for later on when it's at this bigger distance. Now, what are we doing here? Well, I've taken this equation, I've cross-multiplied to isolate power, and then I said if I apply the first conditions at 5 meters and the second conditions at 2 meters, this product gives me the same power because it's constant. And you could solve because we know I1, 30, we know R1, 5, we know R2, 10. The other way to solve is to actually find the value of power. Intensity is power over 4 pi r squared. The intensity initially is 30. R, we know, that's initially 5. And so power we could find by cross-multiplying. Once you find the value of power, plug it back into the exact same equation. But now, we're plugging the value that we calculate in right here. We are seeking a new intensity upon reaching 10 meters, a new distance. So you plug in the power, you plug in R, and you solve for I. Number 2, a source oscillates with a frequency of 1.5 hertz. That means we complete 1.5 cycles per second. Each wave that's produced, each cycle, carries 3 joules of energy. Determine the intensity of these waves at a distance of 2.75 meters. Well, I know that I need this equation for intensity. We're assuming the waves spread out like a sphere, so we can use the surface area of a sphere as our denominator for area. Okay, this is frequency because it's in hertz. This is distance, or the radius of the waves that are spreading out spherically, right? And they reach some point, 2.75 meters away. And we have to find the intensity at that point, given how spread out the wave now is. Well, I know R, so if I want to solve for I, we'll have to find P first. What about the other equation? Power is the energy divided by the amount of time. Well, I know the energy in one cycle, the energy corresponding to one wave cycle is 3 joules. can I find the time for one wave cycle? Wait a second, the time for one wave cycle is just period, right? How is period related to frequency? They are inverses of each other. So the time period is 1 over 1.5, and that's going to be, what is that, 0.67, right? Because it's 1 over 3 halves. It's 0.6 repeating. I plug that in. Here's the time associated with one complete wave cycle, and they gave the energy for one, each wave, that's one wave cycle, has this energy. And what do we get? .5. Power is 4.5. The unit there is joules per second, or a watt. So now I know the power, that's 4.5. I know R, 2.75. I can calculate intensity. The trick here was to realize how to use this equation. We are modifying it by saying apply the equation to one single wave. In effect, the numerator became energy of one cycle, or one wave, and delta t became the time for one cycle, or one wave, which is simply capital T, 1 over the frequency. Number 3, a star emits power given by this equation, which is really intensity, isn't it? I is the emitted intensity at the surface of the star. Here, sigma is a constant, and that never changes, and the temperature of the star is given as 6,500 Kelvin. The radius is this. I'm already starting to think intensity is power over area, or for a spherical star, the area is 4 pi r squared. I know r already, don't I? And I can find I from the equation. What are they asking first? Calculate the surface area of the star. Oh, well, it's a sphere, right? Stars are spherical, and it says assume that. So we use the equation, which is given in your data booklet. The radius of the star is 6.40 times 10 to the 8 meters. And our unit will come to meters squared. Part B, using this formula, find the intensity. Okay. Sigma is 5678, 5.67 times 10 to the minus 8. Then we plug in the temperature, surface temperature, 6,500, and raise it to the 4th power. Wow. You could put that parentheses on the outside of the power if you want. Just the temperature is raised to this power. And you find your answer, just like we did above. Let's see. Part 2 is calculate the power. Oh, well, that's easy. We know intensity, and we know the area at the surface. So we can find the power at the surface, right? We use intensity at the surface is equal to power at the surface over area at the surface. Plug in your answer from above. Plug in the area from above. Cross multiply to get power. Now, the star here is burning out in the middle of outer space. So when it sends out this radiation, the radiation expands, it travels out in all directions. And so after some time, it's spread out to here and so forth. And we want to find the new intensity at this new distance when it has spread really, really far. 10 to the 11, that's way bigger than we started. 10 to the 8 was where we started. So it's way more spread out. We expect it to be less intense. Now here's the thing. We assume the power is constant. And as long as there's not like a planet, a giant planet here, absorbing some of the power, some of the energy, this is a fair assumption. P is constant. So when you get out to this new distance, the intensity, well, it's the same power, but it's now being spread over a much larger surface area because r is much bigger. Plug in the p from above, plug in the r, solve for intensity. Number 4. Here is the speed of sound, that's little c. Speaker is emitting this frequency of waves with this intensity when at this distance r. The waves travel out in all directions. Determine the power. Well, intensity, folks, is power over surface area of the wave. We know the value of I. We know R. Cross multiply all of these things to get power. Determine the energy transported by one cycle. Again, we know the frequency, which is related to one cycle. After all, the time it takes to complete one cycle is 1 over the frequency. So if we use this equation, energy of one wave, one cycle, over the time of one wave, one cycle, we know this, that's our unknown. We know power from above, and we know the time for one wave, it's 1 over 575. Calculate the intensity at this new distance. And again, power we assume is constant. We're not losing energy along the way as it spreads out. There aren't trees in the way. There's not a bird who absorbs some of that energy. It's just, it's all being preserved. But even if the power is all still there, the wave spreads out, so it's less intense as it gets to a larger area. The new intensity is that existing power value from part A divided by the new surface area, the larger surface area. So plug in that new radius, plug in that power, solve for I. Two people shine identical coherent 6 terahertz lasers, capital T, terahertz, that's 10 to the 14, at a point P on a screen. The light travels through air. First, we have to find the wavelength. Well, they gave us the frequency. It's traveling through air, and we know that the speed of light through air is the same as when traveling through a vacuum. Light doesn't slow down in air. It travels at the same high speed, at, almost. So if I know C, and I know frequency, and I seek wavelength, I can just use this equation. Plug in that speed, plug in that frequency, make sure to convert that to regular old hertz, and find lambda. I think lambda comes to 5 times 10 to the minus 7, yes, meters. And if you wanted to convert that into nanometers, it would be 500. Part B, determine whether constructive or destructive interference occurs at point P when the two lasers meet. Well, the path difference, the difference between their lengths is, let's start with the bigger value, it's just easier math, 4.02611137 minus 2.5261134. 4.0261137 minus 2.5261134. 1.5000003. Is that right? 4 O's. 1, 2, 3, 4, 5 O's. Squeeze one more in there. Okay. Here's the question. How many wavelengths is this? Is it 2 wavelengths? No, that's not enough. 5 wavelengths? 5 million wavelengths? Remember what the wavelength is from above. It's this value. We need to know how many times that wavelength, how many times does it go into this path difference? Is it 20? 20 and a half? In other words, what we're doing is we're testing to see, is the path difference equal to an integer times lambda? Or is the path difference equal to an integer plus 1/2 times lambda? Which one? Well, to figure out whether it's a whole number or 1.5, you need to isolate that part of the equation. Let's take delta L, the path difference, and divide by lambda and just see what we get. Is it 10, 5,000, 5,000.5? When we do the division, 1, 2, 3, 4, 5 zeros, and it's 6 times 10 to the minus 7 meters. Let's see what we get. Whoops. Divided by 0.1234567 zeros there, or 7 decimal places. And look at what we have. 2.5 million and a half. That's how many wavelengths go into the path difference. In other words, one wave is like this. It travels, one of these laser lights, one of these waves, travels 2.5 million, and then it travels one more half cycle longer. So when the other wave arrives, because they're a half cycle off or a half wavelength off, it's like this. And destructive interference occurs. It fits the equation. Path difference equals n plus 1/2 times lambda. That's the equation we fit, so we have destructive.